Okay, here's linear algebra, lecture 7. I've been talking about vector spaces and especially the null space of a matrix and the column space of a matrix, what's in those spaces. Now I want to actually describe them. How do you describe all the vectors that are in those spaces? How do you compute these things? So this is the turning the idea, the definition, into an algorithm. What's the algorithm for solving AX equals 0? So that's the null space that I'm interested in. So can I take a particular matrix A and describe the natural algorithm, and I'll execute it for that matrix. Here we go. So let me take the matrix as an example. So we're definitely talking rectangular matrices in this chapter. So I'll have 4 columns and 3 rows. 2, 4, 6, 8, and 3, 6, 8, 10. Okay. If I just look at those columns and rows, well, I notice right away that column 2 is a multiple of column 1. It's in the same direction as column 1. It's not independent. I'll expect to discover that in the process. Actually, with rows, I notice that that row plus this row gives the third row. So the third row is not independent. So all that should come out of elimination. So now what am my algorithm is elimination, but extended now to the rectangular case where we have to continue even if there's zeros in the pivot position, we go on. Okay, so let me execute elimination for that matrix. My goal is always, while I'm doing elimination, I'm not changing the null space. That's very important, right? I'm solving AX equals 0 by elimination. And when I do these operations that you already know, when I subtract a multiple of one equation from another equation, I'm not changing the solutions. So I'm not changing the null space. Actually, I am changing the column space, as you'll see. So you have to pay attention. What does elimination leave unchanged? And the answer is the solutions to the system are not changed because I'm doing the same thing. I'm doing legitimate operations on the equations. Of course, on the right-hand side, it's always 0, and I don't plan to write 0 all the time. Okay, so I'm really just working on the left side, but the right side is keeping up always zeros. Okay, so what's elimination? Well, you know where the first pivot is, and you know what to do with it. So can I just take the first step below here? So that pivot row is fine. I take 2 times that row away from this one, and I get 0, 0. That's signaling a difficulty. 2 2's away from the 6 leaves me with a 2. 2 2's away from the 8 leaves me with a 4. And now 3 of those away from here is 0. Again, another 0. 3 2's away from that 8 is the 2. 3 2's away from that 10 is a 4. Okay. That's the first stage of elimination. I've got the first column straight. So, of course, I move on to the second column. I look in that position, I see a 0. I look below it, hoping for a non-zero that I can do a row exchange, but it's 0 below. So that's telling me that that column is, well, what it's really going to be telling me is that that column is a combination of the earlier columns. That second column is dependent on the earlier column. But I don't stop to think here. that column, there's nothing to do. I go on to the next. So here's the next pivot. So there's the first pivot, and there's the second pivot. Can I just keep this elimination going downwards? So the next step keeps the first row, keeps the second row with its pivot. So I've got my two pivots, and does elimination to clear out the column below that pivot. So actually, you see, the multiplier is 1. It subtracts row 2 from row 3 and produces a row of zeros. OK. That I would call that matrix U, right? That's our upper, well, I can't quite say upper triangular, maybe upper, I don't know, upper something. It's got, it's in this so-called echelon form. The word echelon means like staircase form. It's the non-zeros come in that staircase form. If there was another pivot here, then the staircase would include that. But here's a case where we have two pivots only. OK. So actually, we've already discovered the most important number about this matrix. The number of pivots is 2. That number we will call the rank of the matrix. So let me put immediately. The rank of A, so I'm telling you what this word rank means in the algorithm. It's equal to the number of pivots, and in this case, 2. OK. For me, that number 2 is the crucial number. OK, now I go to, you remember, I'm always solving AX equals 0, but now I can solve UX equals 0, right? Same solutions, same null space. OK, so I could stop here. Why don't I stop here and do the back substitution? So now I have to ask you, how do I describe the solutions? There are solutions, right, to AX equals 0. I knew there would be. I had 3 equations in 4 unknowns. I certainly expected some solutions. Now I want to see what are they. OK, here's the critical step. I refer to it up here as separating out the pivot variables, the pivot columns, which are these two. Here I have 2 pivot columns. Those obviously, they're the columns with the pivot. So I have 2 pivot columns. And I have the other columns I'll call free. These are free columns. OK. Why do I use those words? Why do I use that word free? Because now I want to find the solutions to UX equals 0. Here's the way I do it. These free columns, I can assign any number freely to the variables x2 and x4, the ones that multiply columns 2 and 4. So I can assign anything I like to x2 and x4. And then I can solve the equations for x1 and x3. Let me say that again. If I give, let me assign. So one particular x is to assign, say, the value 1 to x2 and 0 to x4. That was a free choice, but it's a convenient choice. OK, now I want to solve UX equals 0 and find numbers 1 and 3, complete the solution. OK, can I write down? Let's see. Shall we just remember what UX equals 0 represents? What are my equations? That first equation is x1 plus I'm just saying what are these matrices of meaning. That's the first equation. And the second equation was 2x3 plus 4x4 equals 0. Those are my two equations. Okay. Now the point is, I can find x1 and x3 by back substitution. So we're building on what we already know. The new thing is that there were some free variables that I could give any numbers to. And I'm systematically going to make a choice like this, 1 and 0. Now, what is x3? Let's go backwards. Back up. I look at the last equation. x3 is 0 from the last equation. Because x4, we've set x4 to 0, and then we get x3 as 0. Okay, now we set x2 to be 1, so what is x1? Negative 2, right? So that I have negative 2 plus 2, 0 and 0, correctly giving 0. There's a vector in the null space. There's a solution to ax equals 0. In fact, what solution is that? That simply says that minus 2 times the first column plus 1 times the second column is the 0 column. Of course, that's right. Minus 2 of that column plus 1 of that, or minus 2 of that plus 1 of that. That solution is, that's just what we saw immediately, that the second column is twice as big as the first column. Okay, tell me some more vectors in the null space. I found one. Tell me how to get a bunch more immediately out of that one. Just take multiples of it. Any multiple of, I could multiply this by anything. I might as well call it, I could say C, some multiple of this. So x could be any multiple of this one. Okay, that describes now a line, an infinitely long line in four-dimensional space, but which is in the null space. Is that the whole null space? No. I've got two free variables here. I made this choice 1 and 0 for the free variables, but I could have made another choice. Let me make the other choice 0 and 1. You see my system. So let me repeat the system. This is the algorithm that you just learned to do. Do elimination. Decide which are the pivot columns and which are the free columns. That tells you that variables 1 and 3 are pivot variables, 2 and 4 are free variables. Then those free variables, you assign them, you give one of them the value 1 and the others the value 0. In this case, we had a 1 and a 0, and complete the solution. And you give the other one the value 1 and 0. And now complete the solution. So let's complete that solution. I'm looking for a vector in the null space, and it's absolutely going to be different from this guy because any multiple of that 0 is never going to give the 1. So I have somebody new in the null space, and let me finish it out. What's x3 here? So we're going by back substitution, looking at this equation. Now x4, we've changed. We're doing the other possibility where x2 is 0 and x4 is 1. So x3 will happen to be minus 2. And now what do I get for that first equation? X1, let's see, 2x3s is minus 4 plus 2. Do I get a 2 there? Perhaps, yeah. 2 for x1, minus 4, and 2. Okay, that's in the null space. What does that say about the columns? That says that 2 of this column minus 2 of this column plus this column gives 0, which it does. 2 of that minus 2 of that, and 1 of that gives the 0 column. Okay. Now I found another vector in the null space. Now we're ready to tell me the whole null space. What are all the solutions to ax equals 0? I've got this guy, And when I have him, what else goes into the null space along with that? These are my two special solutions. I call them special. I just invented that name, special solutions. What's special about them is the special numbers I gave to the free variables. The values 0 and 1 for the free variables. I could have given the free variables any values and got vectors in the null space. But this was a good way to be sure I got everybody. Okay, so once I have him, I also have any multiple, right? So I could take any multiple of that, and it's in the null space. And now what else? I left a little space for what? A plus sign. I can take any combination. Here's a line of vectors in the null space, a bunch of solutions. Would you rather I say in the null space, or would you rather I say, okay, I'm solving AX equals 0? Well, really, I'm solving UX equals 0. Well, okay, let me put in that crucial plus sign. I'm taking all the combinations of my two special solutions. That's my conclusion now. The null space contains exactly all the combinations of the special solutions. And how many special solutions are there? There's one for every free variable. And how many free variables are there? Oh, I mean, we can see the whole picture now. If the rank R was 2, this is the number of pivot variables, right? Because it counted the pivots. So how many free variables? Well, you know it's 2, right? What is it for a matrix that's m rows, n columns, n variables, that means, with rank R? How many free variables have we got left? If R of the variables are pivot variables, we have n minus R, in this case, 4 minus 2, free variables. Do you see that? First of all, we get clean answers here. We get R pivot variables. So there really were R equations here. There looked like 3 equations, but there were really only 2 independent equations. And there were n minus R variables that we could choose freely, and we gave them those special 0, 1 values, and we got the special solutions. Okay. For me, we could stop at that point. That gives you a complete algorithm for finding all the solutions to AX equals 0. Okay. Again, you do elimination. Going onward, when a column, when there's nothing to be done on one column, you just continue. That this number R, the number of pivots, is crucial. And it leaves n minus R free variables, which you give values 0 and 1 to. I would like to take one more step. I would like to clean up this matrix even more. So now I'm going to go to, this is in echelon form, upper triangular, if you like. I want to go one more step to make it as good as it can be. Okay, so now I'm going to speak about the reduced row echelon form. Okay, so now I'm going to speak about the matrix R, which is the reduced row echelon form. So what does that mean? That means I can work harder on U. So let me suppose I got as far as U, which was good. Notice how that row of zeros appeared. I didn't comment on that, but I should have. That row of zeros appeared because row 3 was a combination of rows 1 and 2. And elimination discovered that fact. When we get a row of zeros, that's telling us that the original row that was there was a combination of other rows, and elimination knocked it out. Okay, so we got this far. Now, how can I clean that up further? I can do elimination upwards. I can get 0 above the pivots. So this reduced row echelon form has zeros above and below the pivots. So let me do that. So now I'll subtract 1 of this from the row above. That will leave 0 and a -2 in there. And that's good. Okay. And I can clean it up even one more step. I can make the pivots I'm going to make equal to 1. Because I can divide equation 2 by the pivot. That won't change the solutions. So let me do that. And then I'm ready to stop. 1, 2, 0, -2, 0, 0, 1, 2. I divided the second equation by 2 because now I have a 1 in the pivot and zeros below. Okay, this is my matrix R. I guess I'm hoping that you could now execute the whole algorithm. MATLAB will do it immediately with the command RREF, reduced row echelon form of A. So if I input that original matrix A, and then I type that command, press return, that matrix will appear. That's the reduced row echelon form, and it's got all the information as clear as can be. What information has it got? Well, of course, it immediately tells me the pivot rows 1 and 2, pivot columns 1 and 3. And in fact, it's got the identity matrix in there, right? It's got zeros above and below the pivots, and the pivots are 1. So notice the 2 by 2 identity matrix that's sitting in the pivot rows and pivot columns. It's I in the pivot rows and columns. It's got 0 rows below. Those are always indicating that original rows were combinations of other rows. So we really only had 2 rows there. And now it also, so there's the identity. Now it's also got its free columns. And they're cleaned up as much as possible. Actually, it's now so cleaned up that the special solutions, I can read off. You remember I went through the steps of computing doing back substitution. Let me, instead of that system, let me take this improved system. So I'm going to use these numbers. Right? In these equations, what did I do? I divided this equation by 2. And and I had subtracted 2 of this, which knocked out this guy and made that a minus sign. Is that what? That's now, I've now written Rx equals 0. Now, I guess I'm hoping everybody in this room understands. The solutions to the original AX equals 0, the midway, halfway UX equals 0, and the final RX equals 0, all the same. Because going from one of those to another one, I didn't mess up. I just multiplied equations and subtracted from other equations, which I'm allowed to do. Okay, but my point is that now, if I do this free variables and back substitution, it's just the numbers are there. When I let x, so in this guy, I let x2 be 1 and x4 be 0. I guess what am I seeing here? Let me sort of separate this out here. I'm seeing in the pivot columns, if I put the pivot columns here, I'm seeing those. And in the free columns, I'm seeing, what am I seeing in the free columns? A 2, 0 in that first free column, the x2 column, and a minus 2, 2 in the fourth column, the other free column, and the row of zeros below, which of course have no, if that equation is 0 equals 0, that's satisfied. Here's my point, that when I do back substitution, these numbers are exactly what shows up. Oh, their signs get switched. I was going to say those numbers, 2 minus 2, 0, 2. Can I just circle this is the free part of the matrix. This is the identity part. This is the free part. Maybe I'll call it F. This, of course, I call I, because it's the identity. The free part is, I'm just doing back substitution. And those free numbers will show up with a minus sign because they pop onto the other side of the equation. So I see minus 2, 0, and I see 2 minus 2. So that wasn't magic. It had to happen. Let me show you clearly why it happened. Okay, so this is what I'm interested in here. And now let me just do it for, let's suppose we've got this system already in our REF form. So my matrix R is, what does it look like? Let me pretend that the pivot columns come first, and then whatever's in the free column. And there might be some 0 rows below. There's a pretty typical reduced row echelon form. You see what's typical? This is R by R. This is R pivot rows. This is R pivot columns. And here are n minus R free columns. Okay. Tell me, what are the special solutions? What's x? If I want to solve Rx equals 0, in fact, I'm really going to do the whole, since this is now block matrices, I might as well do all of the special solutions at once. So I want to solve Rx equals 0. And I'll have some special solutions. Actually, can I do them all at once? I'm going to create a null space matrix. Okay. Matrix. It's columns are the special solutions. The columns are the special solutions. I'm making it sound harder. It's going to be totally easy. N will be this null space matrix. I want R, N, to be the zero matrix. These columns of N are supposed to get multiplied by R and give zero columns. So what N will do the job? I'm going to put the identity in the free variable part, and then minus F will show up in the pivot variables, just the way it did in that example. There we had the identity and F. Here and in the special solution. So these columns there's the matrix of special solutions. And actually, so there's a MATLAB command or a teaching code command, null n equal. So this is produces the null basis, the null space matrix, null of A, and there it is. And how does that command actually work? It uses MATLAB to compute R. Then it picks out the pivot variables, the free variables, puts ones and zeros in for the free variables, and copies out the pivot variables. It does back substitution, but back substitution for this system is totally simple. What is this system? Rx equals 0. So this is R is I, F, and X is the pivot variables and the free variables, and it's supposed to give 0. So what does that mean? That means that the pivot variables plus F times the free variables give 0. So let me put F times the free variables on the other side. I get minus F times the free variables. There's my equation as simple as it can be. That's what back substitution comes to when I've reduced and reduced and reduced this system to the best form. Okay. And then if the free variables, I make this special choice of the identity, then the pivot variables are minus F. Okay. Can I do another example? Could you do another example? Let me just take another matrix and let's go through this algorithm once more. Okay. Here we go. Here's a blackboard for another matrix. Okay. So I'll call the matrix A again, but let me make it, how big shall we make it this time? Why don't I do this? Just for the heck of it, let me take the transpose of this A and see what happens to that. 2, 4, 6, 8. And 3, 6, 8, 10. Before we do the calculations, tell me what's coming. How many pivot variables do you expect here? How many columns are going to have pivots? How many? We have 3 columns in that matrix, but are we going to have 3 pivots? No, because this third column is the sum of the first 2 columns. I'm totally expecting that these will be pivot columns because they're independent, but that this third guy, the third column, which is dependent on the first 2, is going to be a free column. Elimination better discover that. And elimination will also straighten out the rows. We'll also identify some dependent rows and some independent rows. What's the row reduced echelon form for this? Let's just do it. Okay. So that's the first pivot. 2 times that away from that gives me a row of zeros. 2 times that away from that gives me a 0, 2, 2. And 2 times that away from that gives me a 0, 4, 4. Okay? First column is straight. First variable is a pivot variable, no problem. On to the second column. I look at the second pivot, it's a 0. I look below it. There's a 2. Okay, I do a row exchange. So this 0 is now there. I now have a perfectly good pivot, and I use it. Okay, and I subtract 2 of that row away from this row. All right, if I do it like that? I've got to the form U now. This was my A. Now there's my U. I can see now. I have to stop, right? I would go on to the third column. I should have tried. I quit, but without trying. I shouldn't have done that. On to the third column. Look at the pivot position. It's got a 0 in it. Look below, all zeros. Now I'm entitled to stop. Okay. So the rank is 2 again. What about the null space? How many special solutions are there this time? How many special solutions for this matrix? I've got, and which are the free variables and which are the pivot variables and so on? Pivot columns. I've got 2 pivot columns. And that's no accident. The number of pivot columns for a matrix A, that's a great fact. That the number of pivot columns for A and A transpose are the same. And then I have a free column. There's a free column. 1 free column, because the count is 3 minus 2. 3 minus 2 gives me 1 free column. Okay, so now let me solve what's in the null space. Okay, so let's see. These vectors have length 3. They only have 3 components. I'm making too much space to write x. X has just got 3 components, and what are they? I'm looking for the null space. Okay, so how do I start? I give the free variable some convenient value. And what's that? I set it to 1. I set the free variable to 1. If I set the free variable to 0 and solve for the pivot variables, I'll get all zeros, no progress. But by setting the free variable to 1, you see my 2 equations now are, my equations are x1 plus 2x2 plus 3x3 is 0. That's my first equation. And my second equation is now 2x2 plus 2x3 equals 0. And, okay, so if x3 is 1, then x2 is minus 1. And if x3 is 1 and x2 is minus 1, then maybe x1 is minus 1. And actually, I go back to check now. I don't I did a quick calculation mentally. Can I mentally do a quick check? That matrix, that solution X says that minus this column, plus this one is the 0 column. And it is. Minus that, plus that is 0. So that's in the null space. And now you can tell me what else is in the null space. What's the whole null space now? I multiply by C. Right. The whole null space is a line. So that's the description. If I ask you on a homework or a quiz or the final, tell me the null space, find the null space of this matrix, you could take those steps. And that's the answer I'm looking for. And I'm looking for that C, too, because that's telling me that you're remembering that it's a whole space and not just one vector. Later, I will ask you for a basis for the null space. Then I just want this vector. But if I ask for the whole null space, then there's the whole line through that vector. Okay, now, one more natural thing to do with this example, right, is keep going to the reduced matrix, R. So can I push onwards to R? That should be quick, but let's just practice. Let me keep going to R. Okay, so what do I do here? I subtract, I clear out above the pivot, so I subtract that from that. That's 1, 0, 1 is left, right? When I subtracted this row from this, it produces 0 above this pivot. And now I want that pivot to be a 1. So for the R matrix, I'll divide this equation by 2. And of course, these zeros are great. They don't change. There's R. That's R. You see what R is? You see the identity matrix sitting up here? You see the free part F, the F part here? And you see the zeros below. This is I, F, 0, 0. And what's the X? The X has the identity. Well, it's only a single number 1, but it's the identity matrix in the free part. And what does it have in the pivot variables? What did back substitution give? It gave minus these guys. You see that what this is any multiple of, this is the identity there, and this is minus F here. That's our null space. This is our null space matrix N for this. Our null space matrix is the guy whose columns are the special solutions. So their free variables have these special values 1, and the pivot variables have minus F. So do you see how the minus F just automatically shows up in the special solutions? That's it, really. I don't think there's anything more I can say about AX equals 0. There's more I can say about AX equal B, but that'll be Friday. Okay, so that's the null space. Thanks.